In this optimization problem, we're asked to find a maximum area. A fence length is 100 feet. That would be the perimeter. Find the dimensions of the rectangle formed by the fence so the area of land enclosed by it is maximized. Here's our outline for solving optimization problems. Step 1, name the quantity that you want to optimize. Step 2, write an equation relating this variable in step 1 to only one other variable. Step 3, find the first derivative and the critical numbers for that value, that function. And step 4, find the absolute maximum or minimum. In this case, it'll be the maximum. And step 5, draw a conclusion. First, we're going to consider the value to be optimized is going to be the area. So here we have our rectangle. The sides will be x's and y's, and we want to maximize the area inside. Okay, step 2, we're going to write an equation that relates the variable a to only one other variable. So we have a equals x times y, but we need to eliminate one of the variables, x or y. We'll eliminate y using the given information about the perimeter. Perimeter of the rectangle would be 2x plus 2y. It equals the 100-foot length of the fence. Solve for y, we get y equals 50 minus x. So replace y in the area function, a equals x times 50 minus x, and then distribute the multiplication by x. Here we have a polynomial, a equals 50x minus x squared. The derivative of that will be 50 minus 2x. You can factor it as 2 times 25 minus x. Okay, set that equal to 0 and solve. You get the critical number, the one and only, is x equals 25. No more critical numbers, and that's because a is a polynomial, 50x minus x squared, so it is defined on all real numbers. Okay, it doesn't have any points where the function is not defined. Or I should say that about the derivative. The derivative has no values for which it is undefined. Step 4, find the absolute max or min, in this case the max. Again, we're going to use note 93. Since polynomial a equals 50x minus x squared is continuous on all real numbers and x equals 25 is a critical number, we will notice that x prime of x, which is equal to 2 times 25 minus x, is going to be greater than 0 when? When? Well, just look at the factored form, 2 times 25 minus x. That's going to be greater than 0 whenever x is smaller than 25. I mean, plug it in there and look what happens. Now, it'll be less than 0 for all x's that are greater than 25. So we can make our conclusion about this. Thus, x equals 25 is an absolute maximum. We're not interested in the min, just the maximum. Okay, let's draw our conclusion about this. Thus, x equals 25, and for y, use the perimeter 2x plus 2y equals 100. And all we'll need to do is solve that equation for y. We get 50 minus 25, because we let x equal 25, and we get y equals 25. So we have our x and we have our y required to maximize the area. I just want to make a comment about step 4. We could have used note 70 to find the absolute max. For this step 4, selecting a closed interval from 0 to 50. That would have been doable, but this one was actually easier using note 93. So the only correction I see here comes at step 2, where I gave you the because. It's because not a equals 50x minus x squared. We get only one critical number, the 0 of a prime, because a prime equals 50 minus 2x is a polynomial, and it has no values of x for which it's undefined. It's defined on all real numbers.